finding extrema on a closed interval. Our objective is to use the derivative to find the maximum and minimum values of a function. Let's talk about the extreme value theorem. This says if f is continuous on a closed interval, a to b, then f has both a maximum and a minimum on that closed interval. Now, let's take a moment to talk about why this is true. I challenge you to pause the video and try to draw a continuous function on a closed interval that doesn't have any maximum or minimum. Go ahead and do it now. Did you do it? Well, here are some things you might have tried. Closed interval. So that's a continuous function on a closed interval. That's a continuous function on a closed interval. That's a continuous function on a closed interval. In none of these examples did I ever pick up my pencil, and I included the endpoints on all of them. So, do we have a maximum and a minimum value in all of these graphs? Absolutely we do. The highest point here is at that spot. The lowest point is at that spot. In our second graph, the highest is at that endpoint. The lowest is at that endpoint. On this graph, the highest and lowest happens to be the entire graph because it's a horizontal line. There is both a maximum and minimum value of this graph. It just happens to be the same value and it occurs everywhere. So it is impossible to make a continuous function on a closed interval that doesn't have both a maximum and minimum. Now recall that these extreme values, these maximums and minimums, will occur at critical numbers and or at endpoints. So let's talk about steps to locating extreme values given a function and using the derivative. So because max and min values will occur at critical numbers or at endpoints, the first thing we need to do is find all the critical numbers. Then we evaluate the function at the critical numbers and the endpoints and see which is the greatest and least values from those function values. Let's do an example. Find the absolute extrema, so the absolute maxes and mins. I have a function g of x equal 5 sine of 2x on the closed interval 0 to 5 pi over 4. The first thing we will do is find all of the critical numbers. To do that, we're going to find the derivative first, g prime of x. This requires the chain rule, but 5 is a constant multiple, so I'll start by writing that. The derivative of sine is cosine. The 2x stays the same, and then I multiply by the derivative of the inside, which is 2. Where does this derivative equal 0? Well, I can divide by 5 and divide by 2 so that I have cosine of 2x equals 0. Cosine of pi over 2 equals 0, so that means 2x could equal pi over 2. Cosine of 3 pi over 2 also equals 0, so that means 2x, the angle inside the cosine, could also equal 3 pi over 2. Cosine of 5 pi over 2 also equals 0, so 2x could also equal 5 pi over 2, and so on and so forth. Now to solve for x, to get x by itself, I'll multiply both sides by 1/2, and I get that x equals pi over 4, 3 pi over 4, 5 pi over 4, and so on and so forth. Now, my closed interval only goes from 0 to 5 pi over 4, so I don't need any values greater than 5 pi over 4. So we found the critical numbers. Next, we're going to evaluate the function at these critical numbers and at endpoints, because that's where maximum and minimums can occur. So the most organized way to do this is to make a t-table, where we have x values on one side and the y values, the g of x values, on the other side, and we list our critical numbers and our endpoints. So our critical numbers are pi over 4, 3 pi over 4. 5 pi over 4 is also an endpoint, so let's list both of the endpoints, 0 and 5 pi over 4. And we plug them into the original function to see the greatest and least values of the function. Let's make a note in here that we found our critical numbers, which are where the derivative equals 0 or doesn't exist. The sine function exists everywhere. And that we're evaluating the critical numbers and endpoints in our t-table, the most organized way to do it. Plugging in pi over 4 into our g of x function, our original function, we write 5 times sine of 2 times pi over 4, which makes pi over 2, and sine of pi over 2 is 1. 5 times 1 is 5. Then we plug in 3 pi over 4. Sine of 2 times 3 pi over 4 makes sine of 3 pi over 2, which is negative 1, times 5 is negative 5. 5 times the sine of 2 times 0. Sine of 0 is 0, and 5 times 0 is 0. And finally, 5 times sine of 2 times 5 pi over 4, which is 5 pi over 2, which is 1, and 5 times 1 is 5. So now we look for the greatest and least values of these function values, because remember, that's what the max and min mean, the greatest and least values. I see 5 is the greatest of these values. Now, it doesn't matter that it occurs at more than one place. It still is the maximum value. So we'll write that the max is 5. If we want to, we can also say where it's located. So we could say at x equals pi over 4 and 5 pi over 4. The minimum is the lowest, the least value, negative 5. So then we'll also say that the min is negative 5. We can say where this is located at just the one x value, 3 pi over 4. Greatest and least of the function values. In this case, g of x. Let's find the absolute extrema for the function f of x equals 2x minus 1 if 0 is less than or equal to x, which is less than or equal to 2, x squared minus 5x plus 9 if 2 is less than x is less than or equal to 3. Now, in the previous example, the sine function, of course, a continuous function, but a piecewise function might not be a continuous function. So before we go any further, let's begin by verifying that f is continuous on the interval 0 to 3. How do we do that? We'll think about our definition of continuity. First of all, what is the part where it might not be continuous? Because it's a linear and a parabola, each of them on their own is a continuous function. But at x equals 2, they might break apart. So let's take a look and see x can equal 2. So I know that f of 2 exists because f of 2 is 2 times 2 minus 1, which is 3. So I need to check the limit as x approaches 2 from either side. So the limit as x approaches 2 from the left of f of x, from the left is this side. So that's 2 times 2 minus 1, which is 3. And then the limit as x approaches 2 from the right, it's that one. So that's 2 squared minus 5 times 2 plus 9, and that's going to also be 3. So our limit from the left equals our limit from the right, which equals our function value to begin with. So yes, this is a continuous function on the closed interval 0 to 3. Now let's talk about finding the critical numbers. To do that, we're going to take the derivative. So critical numbers, f prime of x and we'll do each piece one at a time. The derivative of 2x minus 1 is 2, and that's for the piece of 0 is less than or equal to x is less than or equal to 2. And then the derivative of this one, 2x minus 5, and that's for 2 is less than x is less than or equal to 3. Now we're looking for where does the derivative equal 0? Now in the first piece, that derivative doesn't equal 0. So on that first interval, 0 to 2, there are no critical numbers because f prime can't equal 0. What about on the second interval, 2 to 3? The derivative equals 0. The derivative is 2x minus 5, so 2x minus 5 equals 0 when x equals 5 halves, 2.5, which is on that interval. So we have one critical number from looking at where the derivative equals 0. Now, we have this possible break-apart point. Well, of course the function is continuous, but that doesn't mean that the derivative exists there. So let's now look at x equals 2. What about at that spot? So let's look at the derivative from the left. F prime of 2 is 2 because the derivative is 2 everywhere on that interval. And then let's look at the derivative from the right. F prime of 2, plugging the 2 into the derivative, 2 times 2 minus 5, that's negative 1. These two values are not equal. So because these are not equal, then f prime of 2 does not exist. So therefore, we have a critical number, x equals 2. Now we plug in to our t-table the x values into the function values. And we've got two critical numbers, x equals 5 halves and x equals 2. So 5 halves and 2. And then we have two endpoints, 0 and 3. Now we just have to be careful that we plug them into the correct spots. So plugging in 2 goes into that first expression. So that'll be 2 times 2 minus 1, 4 minus 1, which makes 3. 5 halves is on that second interval. So that's going to be 5 halves squared minus 5 times 5 halves plus 9, and that equals 11 over 4. 0 is on the first interval, so 2 times 0 minus 1, which makes negative 1, and 3 is on the second interval, so that's 3 squared minus 5 times 3 plus 9, and that gives us 3. So now we're looking for our greatest and least values. It looks like we have a greatest value of 3 that occurs at two different places. So we say our max is 3, and it's located at x equals 2 and x equals 3. Our least value is negative 1. So our min, our absolute minimum, is negative 1, and it's located at that one x value, 0. And there we have it. Thanks for watching.